Hello dear student, welcome on this video. In this video lecture we will be focusing on magnetic properties of matter. So what are the magnetic properties a matter or substance carry? So let's just start from the basic. Let's consider any substance. So that's a substance we are considering, a part of any material, and in that inside of that part, if we look carefully, then what happens, this substance is made up of basically molecules, then atoms, then finally go to this atom level. Then you'll find I'm considering one atom. So if we consider one atom of that particular substance, so in that atom you'll find some positive charges located inside, neutron and proton. And what happens, that the negative charge is orbiting, or electrons are orbiting on the orbits which surrounds the nucleus. So let's consider one orbit, and let's say this electron is there, and this electron is moving, let's say orbiting like this. So if electron is orbiting like this, then you'll find this can be considered a current moving in this way. So that's how it can behave like a current carrying loop, and there will be certainly certain radius. So that means this is going to have an area of that loop and the current. So we can say this will create a magnetic dipole moment, because magnetic dipole moment is a current carrying loop. So that's going to be mu, and mu is going to be I into area. That area can be written as a pi r square, and for the simplicity we can write as A. So that means every electron orbiting along around a nucleus is going to behave like a magnetic dipole moment. And this is for one atom. In one atom you will find there are several electrons orbiting, so that means their dipole moment will be adding up, right? So we can also write this dipole moment by capital M if we want, because we know we can also write it as by capital M. So this magnetic dipole moment will be because of each and every individual atom. And since each and every individual atom carry a magnetic dipole, and then we can connect it, we have understood if there is a magnetic dipole that's equal to bar magnet. That means if the M is known to us, we can find what the magnetic field it is going to create. That means every atom is a magnetic dipole moment or magnetic dipole, and that will have its own magnetic field. So that means all the substance that we talk about carry their magnetic fields because of each and every atom present in them. But if we talk about the substance in totality, then you'll find there are several amount of atoms existing together. When I say several, that means very large number, right? So a large number of these atoms are present. And if we write this dipole moment by a vector arrow, then we will find these dipole moments will be oriented within this material in very random directions. So each and every molecule that you look at, they will not be following any order in general, and they will be randomly located or oriented. So their directions are randomly in this material. So basically these are the vectors. You treat them a vector which are randomly distributed and having random directions. So if we are looking for what is the net magnetic dipole moment is going to be, so we can say the net magnetic dipole moment is going to be equal to, when I write m net, that means net magnetic dipole moment, it's going to be summation of all individual magnetic dipole moments for each and every atom. I for just a number, so let me write it as a j. So this j is indicating like j runs from 1 to large numbers. So that means we need to have the vector sum of all the atomic dipole moments, and this vector sum for random distribution of a large amount of numbers or vectors is always 0. So that means if there is a large amount of vectors which are totally randomly oriented, then their vector sum is always 0. That's the one rule, and that's the rule you might have heard in case of a polarization. So that means a substance is going to have like a 0 dipole moment. That means its total magnetic field will be 0. However, there are certain substances which do not allow it to be zero. That means they align them in a particular direction. Hence, they becomes magnet. So they have a permanent magnetic dipole moment. So that becomes magnet. So we are talking about those substances apart from the magnet. In case of magnet, you will find this won't be non-zero. So this material will start behaving like a magnet, and that we have understood as a bar magnet earlier. And all other substances will have a zero magnet, total magnet, and then they will not have their own magnetic field. However, scenario will change if we create a magnetic field in the surrounding or in that region. So if we place this substance, whatever we have discussed over here, without external magnetic field, let's apply some external magnetic field. So what this external magnetic field is going to do, we can think of. That external magnetic field is going to apply a torque on these individual dipole moments. And we know that torque is given by formula mu cross B or M cross B. Now this torque will be rotating these small dipoles in a particular direction, and then they will be reorienting them, so the direction of these vectors will be aligning in particular fashion. Hence the sum of these vector numbers will not be zero. So when we apply the external magnetic field, then you will find here there will be net magnetic dipole moment creating. So there is going to be net magnetic dipole moment which will not be zero. That means this material will have its own magnetic field because of this dipole moment. And since there is its own magnetic field, hence there is going to be net field other than this external field that you applied. So net field will be, we can say, that is because of the external field as well as because of the field coming because of this bar magnet, or you can say with this magnetic dipole moment, or reorientation of these small dipole moments, right? So how these materials behave, if we consider all the solid materials, then in all the solid materials, whatever the field that comes in because of this is influenced by this, and some of them create a field in the direction of this field, that is the field that you are applying. Some material create a field opposite to this, and some create a strong magnetic field in the direction of the field that you applied externally. So based on their field coming in because of this dipole orientations, we categorize these magnetic materials in three types. So we will be studying those three types shortly. Let me add some more points on this. When we do this, so there's going to be a dipole moment coming in. So what this net magnetic dipole moment is going to be, this can be related with the with one of the important quantity. So we define a quantity called magnetization. So a quantity called magnetization is very similar to the polarization that we have studied earlier in electrostatic. So magnetization is basically talks about how much magnetization taking place because of this external field that we have applied. In case of absence of external field, there was no magnetization because this material was not having its own magnetic field. So magnetization, there are different symbols that are being used, and popularly we use this I later. So magnetization is a vector, and that is denoted by I, and this magnetization is defined as net magnetic dipole moment that is going to be there. So net magnetic dipole moment per unit volume. So that's the important quantity we need to keep in mind. So magnetization is defined as, we can define it as the net magnetic dipole moment per unit volume in any material. So if there is a coming net magnetic dipole moment, that means there is a magnetization taking place, and that magnetization is indicated by I vector. and this I vector is basically going to behave like the field coming because of these dipoles. So once we know what the field is coming because of this dipole, and that field will be magnetized field, and that's going to be external field. Hence net field will be external field plus magnetized field. So we can say a net magnetic field that is going to come in the matter is going to be sum of this external and this. So we can write over here, we want net magnetic field, net magnetic field in the material is going to be equal to vector sum of applied external magnetic field plus magnetization. So this magnetization is coming because of the properties of material, and you are applying a field. So net field is getting as a vector sum of these two things. Now this magnetization, if we talk about the unit of it, we can talk about what the unit of this magnetization is going to be. So this magnetization will have a unit of dipole moment and volume, and dipole, you know, it's area into current. So ampere into meter square, there's a meter cube downside, so we can write it, that is going to be ampere per meter. So ampere per meter is the SI unit of magnetization that we can remember. And this magnetization is caused because of the external field. For instance, here we have seen that this I is 0 because no magnetic dipole moment, hence no magnetization. That means magnetization is caused by external magnetic field. It is very similar to the concept like polarization, because polarization is caused by external electric field. Similarly, magnetization is caused by external magnetic field. Now, since we need to make these two quantities to add up, like applied field and magnetization in vector format, so we would like to write or place this external field or write this external field in such a way that has the same unit that is of magnetization, so that we can add these two in properly, because for addition they should have the same units. So because of that reason, this external field that we apply, we do not write it as a B, because B is a magnetic field, induction or magnetic field that does not have a unit ampere per meter. So we convert it into a different letter that's called H, and this H is going to have the same unit that is of this I. So we can add them properly and we can do further calculations easily. So let's see what this H is going to indicate. So we will be writing this as B. So when we write this B, that's called magnetic field or magnetic induction, magnetic field or magnetic induction. We defined H as well. So H vector, that's going to be read as a magnetic field intensity. So that's also magnetic field. Magnetic field intensity. And or we can call it, this is applied field. So for application external field, we will be applying this thing. And this is magnetic field induction, to be proper. So this is how their names goes. B is magnetic field induction and H is magnetic field intensity, and they are different a bit. So what the difference is, let's talk about, we define this B as let's say this H, because we need to focus on this H. So H is going to be defined as B divided by mu. So if we divide this B by mu naught, then you'll find this will carry the dimension similar as ampere per meter. You can check from Biot-Savart law or otherwise. So this is how we define this H, that is magnetic field intensity. And this magnetic field intensity is going to be whatever the B and that you are applying divided by mu naught. And that is where in vacuum or in space, or you can say without any material, or free space we can call. So this is how they are linked together. Now if we apply B, that means we can say this is equivalent to H. but just by using this mu naught in calculation. Now, if we are applying this H, so material behaves in two ways. So let me, in three ways, we will talk about those three ways. So let me give the general aspect first. So let's say this is material, and here we have applied this magnetic field called H. So that's applied external magnetic field. Because of this applied external field, this will create magnetization I. So how this magnetization is coming? We have seen that there's going to be dipole moments, and that dipole moments will be non-zero, so that will be magnetization. So this is the external applied field. So we will call it as the external field or externally applied field in terms of field intensity. And this is magnetization. So what the net magnetic field will be? So we can say in material or substance, net magnetic field will be given by B. So net magnetic field we are going to write as a B, and that B will be equal to this H can be written in terms, first let me write in terms of this, so that can be written as in terms of H, but this H is going to be having a different unit, right? So this H has to be replaced in terms of with this proper symbol. So this B is going to be equal to mu naught H and this is going to be H plus I. That's going to be the total field that's going to be there. Now this expression that I have wrote is for vacuum, and whatever I'm writing over here, that is for in any material. So if we are talking about any material, so what the net magnetic field is going to be? It's going to be mu naught H because of the field that we applied, plus the field that is coming out from this magnetization. And you can see this field and this field will get added up vectorially, so it becomes H plus I field in terms of those units. But if we want to write in terms of B unit, so what we need to do, we need to multiply it by mu naught, so that becomes net magnetic field in the material. Making sense? So net magnetic field within the material becomes B vector is equal to mu naught H and I is coming because of magnetization. H is the field that we apply, and B is this total magnetic field that is there. If we want to remove this confusion, we can say this is, let's say, B naught. So B naught is the field that we are applying. So corresponding to this B naught, there is H. So B naught is basically mu naught S. So this mu naught H is basically B naught, and this is I because of magnetization. And if we write dimensionally, so this becomes this. So B is the net magnetic field. Now what we are going to do? We are going to first talk about what type of magnetic materials are, and then for each type of magnetic material we need to know what this I is. Once we know what this I is, we can add with H, we can find what the total magnetic field is going to be. Fine. So now we will talk about this types of magnetic materials. So magnetic materials are basically of three types based on their response to the external magnetic field. So if we apply external magnetic field and to respond to that, they can be categorized of three types. So first type is paramagnetic material, paramagnetic substance or material. In this paramagnetic materials and substance, what happens? Let me explain here. And let's say this is this is some material sample that we have taken, and we have applied external magnetic field, let's say in this direction. That's applied magnetic field that we write by H vector. So that's applied field. And when we apply this field, if these small dipoles that we have talked about, they will reorient themselves. And if they reorient in the direction of the field that we applied, but the magnitude of those magnetization or the magnetization that we are getting is small, so this is going to be I. So if I is oriented in the direction of the field that we applied externally, then we say this kind of materials are paramagnetic. So in paramagnetic materials, this magnetization is in the direction of external applied field, and that has a small amount as compared to the field applied. So this type of substance are known as paramagnetic substance. Right, and here another important point is that this magnetization that we are getting because of the external magnetic field, it is directly proportional to the magnetic field that we are having. So this I is proportional to H, meaning is if we apply more external field, more magnetization will take place. If we keep on applying the external field, magnetization will increasing proportionality. Up to the limit, it can magnetize all the dipoles, or that means it can orient all the dipoles in that particular direction. So this is linearly dependent, and that's we are going to talk about later in detail. So, but we need to remember in paramagnetic material, magnetization is directly proportional to the field that we apply, and it is in the direction of the field as well. Then there is a second category of materials. Second category is called diamagnetic material. In this diamagnetic material, if we place these diamagnetic materials or substance in any external field, let me draw here, then how magnetization is going to take place. So let's say this is the magnetic field that we have applied, or applied magnetic field intensity. So these dipoles will be reorienting themselves and creating a magnetization in nutshell. This magnetization comes opposite to the direction of the field that we apply. If this is coming opposite to the field that we applied, then this type of materials are known as diamagnetic materials. So they are known as diamagnetic materials. So what is the difference between the two? Direction of magnetization. And these diamagnetic materials are universal. That means all the materials show this property. No matter which material we are talking about, there is presence of diamagnetic nature always there, right? And paramagnetic are of some type of materials. So that means even the paramagnetic material will have a diamagnetic characteristic. But in nutshell, this will become in this direction. So that means the opposite I that might have arrived is lesser than this one. So in nutshell, it becomes in the direction of H. So what I'm trying to say, this diamagnetic nature is universal nature. That means it is present in all the materials, and a material is known as paramagnetic if paramagnetic nature is more than the diamagnetic nature, and it is known as diamagnetic if it is a diamagnetic alone. Okay. Or another way could be like if it is a paramagnetic, but paramagnetic nature is feeble as compared to diamagnetic, so ultimately it becomes diamagnetic. So diamagnetic is present in all the materials. Here also this magnetization is directly proportional to the field that we apply. That means more the magnetic field, more the magnetization is going to take place in diamagnetic materials. So these are the two types, and there is a three types called ferromagnetic materials. These materials we are studying based on their response when we apply external magnetic field. The third is called ferromagnetic material. In case of ferromagnetic material, what happens? Again, it will be there's going to be magnetization when we apply a field, but they are entirely different. If we apply this magnetization, if we apply this external magnetic field, then you'll find a strong magnetization will take place. Sometimes this magnetization will be more than the field that you applied. So if there's a strong magnetization is taking place and in the direction of the applied field, then we call such material as a ferromagnetic material. So they are called ferromagnetic material. So here H is in the same direction, or I is in the same direction of H. Here this proportionality relation doesn't valid. So they follow a very different method or relation between these two quantities. So we will see what that relation is, and but we need to know there's going to be strong magnetization. So sometimes people may ask you what is the difference between paramagnetic material and ferromagnetic material. So you'll say in ferromagnetic material and in paramagnetic material, magnetization is in the direction of field that you apply. So that's the similarity. And what is the difference? Difference is that in paramagnetic material, magnetization is small, whereas in case of ferromagnetic material, magnetization is very, very strong. Right? And we will see, even if we remove this, there will remain some magnetization in ferromagnetic material, whereas this is not true for the paramagnetic material. As soon as you remove this H, that means you make H 0, I becomes immediately 0, because they follow the proportionality relation. So when H becomes 0, I becomes 0. But they do not follow the this proportionality relation. So even H becomes 0, I remains there. I can give you one example and you can relate it better. You might have seen this bar magnet or some magnet, and let's say iron coin. So if you touch this iron coin with the magnet or keep in contact for a longer time and then remove the magnet, you might see that that coin is having magnetic properties. That means that coin may be attracting to another coin, just like a magnet. So that was the same case when you place that coin with the external field, that means external bar magnet or magnet. So over the time it got magnetized, and that magnetization was so strong, even you took away the magnet, then the coin carries the magnetization, that means magnetic field. Hence it is attracting to other iron or similar type of metals. So since iron is a ferro, that's what we are talking about. So they are having the ferromagnetic properties. Right? We will see them in more detail. So this is the type of three types of materials: paramagnetic, diamagnetic, ferromagnetic. They have a lot more other properties that you must go through from standard book SCV and see what are other differences. What are the differences that we are talking over here are some important ones which are critical for examination. And to get a holistic picture, you must go through from standard book. Okay. Now we will talk about a little more regarding to this, how this proportionality goes, and if this is not proportionality, so what kind of relation they share. So this relation we need to know. So let's move ahead. Since both for paramagnetic materials and diamagnetic materials, we have seen that the relation is between this magnetization and the field that we applied is of proportionality. So for those, this formula is going to be true, or this relation is going to be true. So we say this I can be written as some constant of proportionality and H. So this becomes an important relation for both paramagnetic as well as diamagnetic materials. So for paramagnetic materials and diamagnetic materials, I is written as zeta. We read it as zeta times H vector, and this zeta is proportionality constant, and this zeta is known as it draws like this. So this zeta is known as susceptibility of the material or medium. So this zeta is called susceptibility of the medium or of the material. So the susceptibility is, if it is known to us, we can place here and we can find the value of I if H is given to us. Now we have already understood that this I and H have the same direction for para, and for dia they are opposite. So we can say what is going to be happening for this para. So for paramagnetic material, we will find the susceptibility has to be positive. Susceptibility has to be positive. Hence the direction will be identical. Similarly, for diamagnetic materials, this magnetic susceptibility is going to be negative. So this magnetic susceptibility is negative. And for no medium, or let's say for vacuum, if we talk about the vacuum, so what will be the case for the vacuum? In vacuum, you will find this magnetic susceptibility is 0, because magnetic susceptibility is 0, then I will be 0, and we know this I is only if there's a H available. That means H is there, or in vacuum, even if we apply this H, in vacuum, even we apply this H, still you will find this I will not be there, because in vacuum there's no molecules, no atoms, so no dipole moment, so no reorientation, right? So that means for vacuum, zeta is 0. So these numbers we can remember. And this can also be demonstrated or explained by using a graph. So many times this graph is being asked. So what is this graph is going to look like if we plot a graph between two quantities? That means between this magnetization that we are getting and the field that we are applying. So we apply the field, we get the magnetization. So how the magnetization we achieve when we apply the field in different materials. So let's say we are drawing for paramagnetic materials. So how it's going to look like for a paramagnetic material? You can say this is going to be this relation. So I is equal to x or zeta to be precise, and h. And zeta is a positive, so it's going to be a positive slope case. So this is going to be the case. And in case you are plotting for diamagnetic, then you'll find the slope will become negative. That means it's going to go for the negative slope. Moreover, so here we can say, if we can measure this angle theta, so can we say the slope is going to be tan theta? Yes, slope is going to be tan theta. And we can also relate with this that this is going to be, slope is also given by magnetic susceptibility. So magnetic susceptibility is basically the slope of I versus H graph for both the cases, whether this is of para case or whether it's of diamagnetic case, right? So this graph is important, has been asked in examination many times. So slope is given, gives the susceptibility, magnetic susceptibility, and this also indicates that I and H, they are linearly dependent for paramagnetic case. Similarly, for diamagnetic case, the only difference is the susceptibility is going to be negative. That means slope will become negative. That means the line will be towards downside. So this is how magnetization is calculated for paramagnetic and diamagnetic materials. Now, once we have calculated these values, like we have talked about this magnetization, now we can find out what the total magnetic field is going to be in the material. So net magnetic field will be given by this. We can say net magnetic field within that material, whether they are para or dia, that will be given by this formula. B is equal to mu naught H vector plus I vector. So that's true for all type of materials. Now here we are able to find this H vector, this I vector. So since we are able to find this I vector, so we can rewrite it. So it's going to be mu naught H plus I. In place of I, we are writing it as zeta times H. Now we can take this mu naught and H vector outside. Then we will find in bracket it's going to be 1 plus zeta, and this becomes H vector. So this will be the formula valid for both paramagnetic and diamagnetic materials. So in short, we can write it in this manner. So B is equal to the net magnetic field is going to be given by simply mu and H. When we are writing it as a mu and H, that means this mu take care of the material in which we have applied the external magnetic field. And this mu is given by mu naught plus something. So this mu can be written as, let me write over here, where mu is written as mu naught into mu r. And further we can say this mu r is equal to 1 plus zeta. So this is how we can write different mu's. Mu is called permeability of space or material. So mu is permeability of material, mu naught is the permeability of free space, and mu r is relative permeability. So if relative permeability is given to us, we can multiply with mu naught to get the effective permeability of that material. And if we got that effective permeability of that material, that means we can use this formula and we can directly write what the B is going to be. So these formulas are valid for paramagnetic as well as diamagnetic material, we need to keep in mind. And mu r is indicating the relative permeability, and zeta is magnetic susceptibility. And from here we can say for paramagnetic materials, mu r is more than 1 because zeta is positive. And for diamagnetic materials, mu r is less than 1 because zeta is negative. And for vacuum, mu r is 1, so this becomes 1. So for vacuum, it becomes mu naught. So you can connect all these three cases that I have listed over here. And this slide talks about entirely for paramagnetic as well as diamagnetic. Basic difference is the sign, and this graph is also important. Now, as a last point, we will talk about the relationship between magnetization and the field applied in case of ferromagnetic material. So let's talk about that. So for ferromagnetic materials, the relation between magnetization and applied field is given by hysteresis loop. So there's a loop called hysteresis loop. So that hysteresis loop describes the relation between I and H. How it describes, let me explain that. So let's say this is a ferromagnetic material that we are having. So that's a sample of that material. And we are applying a field H. Let's say we are applying a field H, or in the field we are placing this. And then we will be studying how this I is going to behave with that field. So that's going to give us the relation between H and I. And if we plot this in such a way, so that let's say H is being plotted in horizontal axis, this graph is going to help us to understand that thing. And let's say this another axis is indicating this I, that is magnetization. We need to see how it happens, how I comes in when H is being applied and changed. So initially, if there is no H initially, and then there will be no I. So that means it will start from somewhere origin. And when we increases this H value, then you'll find this I value increases. Moreover, this I value is not increasing linearly. So it does not go like this. Rather, it increases rather faster. So, and it goes some sort of this. So that is initially when there's no field and the field H is being applied, and then I is getting induced or magnetized. Now when how this I comes, so far you must have understood that this I comes because of reorientation of these dipoles. Once all of them dipoles are getting reoriented, then no matter how much this HU increase, I cannot increase because all the dipoles has come into play and they are contributing to this I. So you'll find that after some time reaching to this point, then after this H, if you increase further H, so you will find this will become this straight line, because now we cannot increase this I by increasing H. So we call this as a saturation. So this point which I am indicating by A, so that's called saturation point, and this is the saturated I. Beyond this we cannot have any more I. So this was the field that we started applying in this direction and increasing H. So we got to the one limit. Now let's decrease this value of H, keeping in the direction of this. So if we start decreasing this value, that means we are moving. First we have gone from here to here. Now we are moving in the backward direction in terms of H. So if we reduce H, so this is not going to follow the old path to come to 0. This is not going to case in case of ferromagnetic materials. Whereas in case of para and diamagnetic material, if we increase H, I increases. If we decrease H, I decreases, and it remains proportionality. So here you will find, even if we decreasing H, then you will find this will be following this path. That means you will be having, or you will be getting magnetization mode all the time. And even if you make this H0, then you will find magnetization will be amount of this. So this is denoted by B point. That means even H has been made 0, then there will be magnetization in the positive direction by a significant amount. So that's called retentivity. Retentivity means this is the amount of magnetization that the material retains even after H has been made 0. So that's called retentivity. So we need to remember that point and terminology. Then what happens? Now let's after making it 0, we start applying it in opposite direction. So we start increasing in the opposite direction. Then you will find this will I will be reducing, but still remain positive. And you will be needing a particular amount of H. This amount of H you need to apply in order to make this I0. That means once this I has come into play, then H0 will not make I0. In fact, H has to be in opposite direction by certain amount to make I0. So this is called coercivity. So this length is called coercivity. That means you need to coerce. That means you need to place this opposite in order to make this I0. And whereas this length that we have talked about is called retentivity. So these two terms are very, very important, and from here you can see that. Then after, if we keep on increasing this H in the opposite direction, negative direction, so we are moving in this direction further, then you'll find this I will be starting developing in the opposite direction. So this I will become negative then after, and will be moving ahead. That means if you are increasing H, this I value is increasing. That means now the dipoles are orienting in this direction, in the direction of the new field. And after certain value of H, after this value of H, you will find all of the dipoles will be oriented in that direction. So no more dipoles are available. Hence you will get this as a saturation value of magnetization. So that's a saturated magnetization. Then after, even if you further increase this value of H in this direction, there will be no other graph is coming. It will be saturated one. I will not be going downside anymore. Hence what we do, we come back again. So we return back. That means now we are keeping this H in the negative direction but decreasing. So when we decrease, again this graph does not follow the old path that it has followed earlier. Rather it's going to follow a different path. So it's going to go like this. And when you make this H0 again, then you'll find this much amount of magnetization will remain in the opposite direction. So that's also going to be known as retentivity. So retentivity is the case, or we can say retentivity is the amount of magnetization that a ferromagnetic material retains even if this H or applied field intensity is made 0. And then after this point we are keeping this H or making this H in the direction of positive and increasing. So if you increase this H in the positive direction, then it is going to increase again rapidly. And when this H will be of this amount, then this I will become 0. So I becomes 0 at this point in the positive direction. This is called coercivity. So this is positive direction coercivity, and this is of negative direction coercivity. And then even if you repeat the same thing, keep on increasing H in this direction, then this will be increasing rapidly and getting saturation very soon. So when it gets saturated, that means it is completed and all the dipoles have aligned again in that direction. And again, if we want, we can repeat this loop. That means we start reducing this H, then this will follow the above path again and come to this, and then if we change this opposite direction, then this is going to follow this path. That means this I will be varying with respect to H in this type of loop, and this loop is known as hysteresis loop. So in hysteresis loop you'll find I and H, they are complicatedly related. But yes, one thing is sure, that if we increase this H, then I value increases and then becomes saturated, then we reduce it, that reduces slowly. That means it retains a certain amount of information regarding this magnetism, then if H becomes 0, then still there will be some amount of magnetization present, that is known as retentivity. And then to make this I 0, you need to apply the field in the opposite direction, that's known as coercivity, and the same occurs in the opposite direction as well. So this is called hysteresis loop, and that's true only for ferromagnetic material, not for para, not for dia. And with this graph or loop, we know what the relation they are sharing, right? So that's an important point. So this hysteresis loop is very important, and we need to know what these numbers are. Particularly, we need to know what the retentivity and coercivity is, and how this graph is, what is the saturation levels, and all that points, right? Now, if we look this in terms of physical point of view, so when this H is, let's say, pointing in this direction, so magnetic dipole moment will be in this direction. And if we changing this H, then this magnetic dipole moment is reorienting later on in this direction, opposite direction. So this magnetic dipole moment basically is keep on changing its direction. If H is fluctuating, that means H is changed periodically. So due to change of this magnetic dipole moment direction, we know this experiences a torque. So that means somebody must have applied torque on these magnetic dipole moments in order to change their orientations. And if some torque is being applied and rotation is taking place, so there has to be some work done. So work done is going to be equal to, or written by this, tau d theta. Now, since there is a work done, that means from somewhere energy has to be given for the purpose of changing this orientation of magnetic dipoles. So that means these ferromagnetic material consumes energy. They need energy in order to change this magnetic dipole moment's direction. If H is changing, that means external magnetic field is changing. So we can say when we place a ferromagnetic material in a variable magnetic field or changing magnetic field, particularly periodically changing magnetic field, then you will find there is going to be some energy consumed by the material themselves. So that energy is basically going into waste, and that is of no use, because that is going for internal rotations of these dipoles. So we call them as a loss, and whatever this loss is, that loss is called as hysteresis loss. Hysteresis loss. So someone can ask you, what is a hysteresis loss? Then you can say, when we place a ferromagnetic material in a variable magnetic field, then the magnetic dipole moment has to change their orientations. For that to happen, some work has to be done, and this work done will require some energy. So that energy will be used in work done, hence energy will be lost. So that's called hysteresis loss. So this is energy loss due to changing magnetic field or applied field. Whatever the energy loss is called, that's called hysteresis loss, and that do occur in case of ferromagnetic materials. And we can relate this hysteresis loss with this hysteresis loop. So whatever this loop you can see, the loop which is running from this A point to B point to C point to D point, then E, F, then coming back to A point. So this loop will have some area inside. So if we can measure this area, we can find what the loss is going to be. So this loss is directly proportional to the area inside the loop. So that's another important point we need to keep in mind, that hysteresis loss, that is loss of energy, is proportional to area of hysteresis loop. Hysteresis loop. So if more the area, more the loss is going to be. If less the area, less the loss is going to be. So in examination, you will be given two types of loops, and you need to find in which the losses is higher. So you just need to see which area is more. More the area, more the loss will be. Less the area, less the loss will be. and this loss is called hysteresis loss. So sometime you might be asked to compare hysteresis loss between two particular types of materials. One is steel, another is soft iron. So question might be asked, in many cases like in transformers or in MCZ, we use soft iron as compared to steel. So why we prefer to use soft iron rather than steel in certain or in this magnetic devices? So you'll find for soft iron, this hysteresis loop area is going to be small as compared to the steel. So you'll find in steel hysteresis losses are going to be higher. So in steel you'll find hysteresis losses are higher. In soft iron losses are small as compared to the steel. Hence we prefer soft iron as compared to the steel in magnetic instruments like transformers and MCZ and other similar type wherever we require a ferromagnetic material to place in. So soft iron is preferred as compared to hard iron or steel because their hysteresis loss is less. That means if we need to draw the loop and compare the loop of steel and soft iron, we can say this loop will be having a small area as compared to this steel loop. Okay, so if there the loops are given to you and asking that one is steel and another is soft iron, compare. So the bigger area will be of steel, smaller area will be of iron because losses are more if the area is more. Makes sense? So this is about ferromagnetic material. So we have just talked about paramagnetic material, ferromagnetic material and diamagnetic material, and we have understood how to link these two things in case of these different type of material. And one last point that we need to discuss is about temperature dependency of this eye, how this eye can be influenced based on the temperature. So this next point is named as Curie Law or Curie's Law. So what is a Curie Law? It's basically related to the temperature variation in case of magnetic properties. So if we vary the temperature, how this magnetic materials behave. So we will be talking about paramagnetic materials. So paramagnetic materials. So let's say we have a paramagnetic material and we are increasing its temperature. This temperature is absolute temperature, Kelvin temperature, and you are heating this material. We know whenever we heat any material, so inside molecules they vibrate and their randomization increases. So increasing the temperature, randomization increases. And we have already talked about that dipole moments are going to be placed like this. So if we have placed this paramagnetic material, let's say in any external field, applied field, so they will align, they will have this magnetization in the direction of field itself. And this magnetization we have understood that is coming because of this formula. That means it uses net magnetic dipole moment divided by volume. Now since temperature increase randomize these molecules, so because of that randomization, this m vector and whatever this vector m net is, this will reduce. Why it will reduce? Because their directions will not be aligned, rather they will be a little more randomized. So on increasing the temperature, m decreases. Because of decrease in m, I decreases. Because of this decreasing I, we call that magnetization is decreasing. And for paramagnetic material, we already know this I is proportional to, this is proportional to, or we can simply write this is equal to susceptibility into H. So I is equal to magnetic susceptibility into H. H is the field that you have applied, and you will find in nutshell I will decrease. So this I decreases because of the decrease in the zeta. That means magnetic susceptibility. So from here we can say magnetic susceptibility decreases when temperature is increased, right? Hence this magnetization decreases. So the Curie law relates this magnetic susceptibility with this temperature, and the relation is very simple, and that relation is this magnetic susceptibility is inversely proportional to temperature. inversely proportional to temperature. That means if the temperature of paramagnetic materials are increased, or we can say paramagnetic materials are heated up, then you'll find magnetic susceptibility will decrease, and because of this, magnetization will decrease. And this is called Curie's law, which we can write in this manner as well. This magnetic susceptibility is going to be C, which is called Curie constant, divided by T. T for temperature. This temperature has to be written in absolute scale. Absolute scale means it has to be written in Kelvin. So this is an important aspect to know about paramagnetic material. So whenever the paramagnetic materials are heated up, their magnetization decreases because magnetic susceptibility decreases, and it is reciprocal to temperature. Then we can also talk about another types of material, that is ferromagnetic materials. What happens to this ferromagnetic materials? Now if we heat these ferromagnetic materials, no matter which material we are heating up, their randomization increases. Because of this increasing randomization, this M value decreases, hence I decreases. So we can say if we heat the ferromagnetic material, then their magnetization is going to decrease. Because of decrease in that magnetization, they will be coming towards paramagnetic materials. So if we keep on increasing the temperature of ferromagnetic material, and then they will be acquiring the properties of paramagnetic material, because we know in paramagnetic and ferromagnetic difference is only of the magnitude. In paramagnetic materials, magnetization is small, and in ferromagnetic material, magnetization is large. But on increasing temperature, magnetization is decreasing. So that means there will be a turning point of temperature. At that particular temperature, you'll find this ferromagnetic material will get converted into paramagnetic material. So that point is called Curie point, and that temperature is called Curie temperature. So we can write over here, in short, if temperature is increased of ferromagnetic material, then magnetization decreases at a particular temperature. At a particular temperature, when you are heating it up, let's call that as TC. This is called Curie temperature or critical temperature, and Curie point. So at a particular temperature, the substance converts from ferromagnetic material to paramagnetic material. So it goes from ferromagnetic characteristics to paramagnetic characteristics. So this transition is taking place. That means ferromagnetic materials now becomes paramagnetic materials. That means whatever the permanent magnetism it carried, it loses that permanent magnetism and it becomes paramagnetic material. So this TC is called Curie point temperature. Curie point temperature, or that point is called Curie point. And then you'll find if you increase the temperature further beyond that, so it becomes paramagnetic material. And this para nature, so we can write over here, for temperature becoming more than Tc, now material becomes paramagnetic material. And this paramagnetic material will have susceptibility dependence on temperature, because again, if you are heating up, its susceptibility is decreasing, and that goes like this. The susceptibility is equal to this Curie constant divided by T minus Tc. So this formula has to be applied for the cases when a ferromagnetic material has got converted into paramagnetic material and temperature is more than the Curie point temperature. Then the susceptibility goes like C upon T minus Tc. This Tc is a critical point or Curie point where this turns from this ferro nature to para nature. Understood? So these 2 points are extremely important, and they are the first is called Curie Law, and this is also related to that Curie point. So here susceptibility is reciprocal to temperature for paramagnetic material. Keep in mind, for ferromagnetic material, we do not have this kind of relation for ferromagnetic material, no. But yes, if the temperature is increased, then I decreases, and at particular temperature this transition takes place. When this transition takes place, then it becomes paramagnetic material. And then again for paramagnetic materials, susceptibility is C upon T minus Tc, because we know this magnetic susceptibility we have talked about for para and dia. For ferro, there is a hysteresis loop that decides how this I and H are related. Understood? So this explains the dependency on temperature or heating effect on the magnetic material. Well, so that's all in this particular video. We have talked about a lot more important points related to magnetic property of matter, and I will again advise you to go through from a standard book and go through the theoretical aspect. It's more like theory, and whatever the important aspects are, we have covered in this particular video. Okay, so that's for all. Thank you for watching. Have a great time.